Okay, a few months ago, I made a tutorial on the concept of virtual parts in CATIA, but primarily those were dealing with static analysis. How do you use virtual parts in static analysis? This current video that I'm doing is using virtual parts for modal analysis, which is really a dynamic analysis. Dynamic. Now, the one that I'm doing right now is on rigid virtual part, and then later on I will do one which deals with rigid spring virtual part, both of them used in the context of modal analysis. So here's the situation. We have a, a part like that. This is drawn as if it's a beam, looks like a beam. It's clamped at the right end and free at the other end. I'm assuming the half of this beam, for example, is the part that's attached to the clamped end is given there. And then the part on the left side, the piece on the left side, it's significantly more rigid than the one, the yellow one. For example, the Young's modulus of it may be 100 times bigger or 10 times bigger. That being the case, the deformation of the gray portion of the part, this beam, is much smaller and negligible compared to the one on the right, the yellow one. Okay, so the way we're going to model a problem, we pretend that this gray one, 100 millimeter, is basically a rigid object, a rigid mass, and we're going to place the mass associated with that gray piece at the centroid of it. So what is shown on the right side is actually the yellow piece, which is going to be modeled with 3D elements, for example, and then we're going to create a virtual part which is shown here, whose handler point, that point, is 50 millimeter away from the face on the right. Now, the reason how I came up with the 50 millimeter is that the centroid is this piece of this piece that we are ignoring is 50 millimeter away from the right end of it. Okay. Now, of course, the mass of this piece that we're ignoring, we're going to place it as a lumped or structural mass at the handler point. Okay. All right. Now let me remind you that when I did the static videos on virtual parts, I showed you this toolbar, and the particular one that I'm using is going to be the rigid virtual part, because we said that this gray piece that we are not actually modeling, because we know it's fairly rigid compared to the yellow piece, is is a rigid part. So rigid virtual part. Okay. All right. Let's move on. Let me give you some dimensions here. So I'm gonna do this thing for you on CATIA in just a few minutes, but I'll show you the dimensions here. So the length of the piece that we model is 100 millimeter. The handler point is located at 150 millimeter from the clamp, or 50 millimeter from here. The cross section is 10 millimeter by 10 millimeter. Here is some data that's given to you. These are more or less properties of steel. Now, the weight based on this density, the mass of this piece, is the piece that is ignored over here. I'm using the same density, but we're assuming it's the same density, but a lot stiffer. Okay, so based on this density, the mass of the piece that we're ignoring is actually 0.079 kilogram, which incidentally happens to be the mass of this yellow one, but that's irrelevant. Okay. All right. Now, let's move on. Now, this particular problem where you have a cantilever beam with a mass at the free end can be modeled, and it is modeled as a single degree of freedom, very crude approximation, in many vibrations books. Okay, so basically that beam that beam acts as a cantilever beam acts as a spring. It has some kind of a mass that we have to incorporate, and the natural frequency of it can be estimated from the well-known single degree of freedom model, which is square root of k over f. Okay. Now I'll show you that based on the numbers that I'm using, this will be 221. Okay. Now, remember, this is a vibration, single degree of freedom vibration solution. We are trying to do this problem and then compare it with this 221, at least to some extent. Now, the one that you see in most vibrations book, the beam is here, the yellow one of length L, mass of the beam is M. Okay, mass of the beam, M beam, and the lumped mass is exactly at the free end, it's attached immediately on the left side to the beam, with the lumped mass of M end. Okay, now the stiffness of this beam, the stiffness of this beam in the vertical transverse direction comes from strength of material formulas, formulas which is C I over L cube. Now, uh, if we, I just want to point out to you, if we ignore the mass of the beam, there is no problem. Just M effective is going to be Mn. But sometimes the mass of the beam cannot be ignored because actually it's substantial. So in vibrations book, they have shown you that you don't add M beam to this thing, but 33 over 140, which is about 0.3, about 30%, 32% of the mass of the beam. Okay, so this comes from vibrations book, but the case that we have is actually mass is not immediately on the right end of this end, but there is a, a rigid piece in between. Now remember, my L bar, when you compare it to the stuff that I showed you earlier, is 50 millimeter. So I've done the calculation, extended the result of these simple vibration formulas to the case where there is a rigid piece in between it, and it comes out to be not only, it's not only Mn that you have to add, but you have to correct it by this factor. Remember, if L bar is 0, in other words, this red piece is immediately attached to the yellow piece, then of course it's going to be Mn plus 33 over 140 turn M of the beam, even based on this. Now, based on the data that I have, the second year vibrations course formula, single degree of freedom, will give you 220 hertz. Now, some of the stuff, Thomson is a well-known vibrations book, so some of these formulas that I gave you can find it there. This gentleman, former student, also has done, Hamoon has done some work along this line, but some of the stuff also can be found in this conference paper. Okay, so now I'm going to go and do this thing with Katia. Okay, all right. So we already have a part here. So let me make the 10 millimeter by 10 millimeter cross section on that plane. So let me see. Okay, let's get some dimensions here. These are both going to be 10 millimeters. Exit, and we pad it by 100 millimeters. That's the yellow piece that we're creating. Okay, let me make this thing yellow right there. Okay, now I'm going to create the 100 point of the virtual part at 150 millimeter from the clamped end, which is over here, or 50 millimeter from the side. So let me do it from 150 millimeter from the clamped end. 150 there. This is going to be the handler point of the virtual part. Let's apply material properties on it. So metal, and I think I use properties of steel. Let's do that. Okay, just to make sure, let's go to properties of steel here. Default properties of steel. Notice that this is 200 2 gigapascal. This is 2 gigapascal, and I'm sorry, not, is it 2 gigapascal? Uh, 200 gigapascal, not 2 gigapascal. 200 gigapascal. I just realized that obviously there was a mistake. There was a mistake here. This, let me see now. This should have been. This should have been 200 gigapascal. Yeah. That number 221 that I showed you was correctly actually calculated. Okay. So this was a mistake. It's not 2 gigapascal. It's 200 gigapascal. Okay. Good. This is 200 gigapascal default property, and this is the density of steel that I use. We don't need these other things. Okay. Good. All right, so now we're going to go to generative analysis and simulation, generative structure analysis. We're going to do a frequency analysis. I'm going to change the size of the element to be, first of all, parabolic and 2 millimeters. So it's small. We don't have a issue of mesh conversions and things like that. And if you want to look at the mesh right here, okay, deactivate this. All right. Now, first thing we're going to do is we're going to clamp this end. This end is clamped. Okay. And then we're going to create a rigid virtual part. There is the toolbar for virtual part elements. Rigid is right there. This is rigid. See that? It's a rigid virtual part. You click on it. It asks for the support. The support is this end. And it asks for the handler point. This is the handler point. This is my virtual part. Okay. And now we're gonna place a structural mass at this at the handler point. Now let's see. Now this is for the toolbar for masses. The first one, distributed mass. The support is this virtual part, and the value is 0.079. I already ran this thing, so Katia remembered that I used 0.079 before. There we are. And let's look at it closely. So there is the mass. You see this lumped mass. Now, just to let you know that it is possible to put surface slider on this side and that side. This is so that the bending out of plane is prevented. Out of plane means for example, out of the um, exit plane. So going towards Y, because the frequency in this particular problem, you will see that there's going to be two identical frequencies, because this can go in the upward direction, transverse direction, vibrate in the exit plane, or it can vibrate in the XY plane. If you want to take out the XY plane vibration, we can put surface slider on the two sides, on this side and on the other side, and it's going to do that. But I'm not going to worry about it, okay? So let's go ahead and run it. We want this. We're going to run it. It's going to give us not only transverse vibration, it's going to give us in both planes, it's going to give an axial one, it's going to give torsional one, which is really not of interest to us. We're just interested in modeling the transverse vibration. So let's see now. Here, right there, you click on deformation, and in fact, you can animate it. You see that? This is vibrating in the or you're oscillating in the exit plane. All right, so let me close this, double click on this. These are all the frequencies that are calculated. Notice that this is the one that I showed you. This is exactly the same frequency can vibrate in the XY plane, and any one of these that you see, there are multiples of them twice, because they can do the vibration in two planes. Okay. Now notice that the only one that we can use for comparison purposes, of course, is going to be with a single degree of freedom is this top one or the second one, and it's pretty in good agreement with the 221 that I got based on single degree of freedom formula. Now you can also model that entire thing as an assembly. So this 100 millimeter, exactly like we did, the other 100 millimeter also as another part with a stiffness that's modules is 100 times bigger, but the stiffness or the density is the same, and and then they create a connection between the two faces and make that fasten. We can extract the natural frequency is going to be very close to what we got. So you can see that the virtual part, the advantage of virtual part is that I don't have to model this very rigid piece. Why would I do that? Because if it's rigid, it's not going to do anything. We created it as a virtual part. We did not create the part. We created a virtual part, and we placed the mass of that at the handler point. Now, if I had used the handler point to be on this face, the default handler point is at the centroid of the support, then it would have corresponded to the problem on the top. If I had not created a handler point at 50 millimeter away from this end and instead used the default one, which is the centroid of that face, essentially I would have solved this problem. And I'll let you do some experiment with this and see that actually the value of L significantly change the natural frequency. In other words, if you had done it like this, my guess is that it was around 350 hertz. Okay, where this one is 200, almost 215 or 221, depending on what you take as your reference. Okay, so the next one, the next video on this visual part and damping is going to be where although I will not create that gray piece that I showed you, that portion, but I will take its stiffness into account because it could be that the stiffness of it is not very, out of whack with the stiffness of the yellow part. Okay, all right. I hope this was useful.